Hi, this is going to be the last video series on 2E04 digital and analog circuits. So this is an overview of the digital design project, which is to get a 7-segment display to output your student number. So we're going to be using displays and decoder chips there. And the key factor of this design project is we're not just going to make the 7-segment display output the student number, but we're going to do it using sequential logic design. So what that means is the inputs from the inputs to the 7-segment display are going to be all the outputs of flip-flops, or possibly just a constant if you're lucky enough to have something held to ground, or maybe a logic gate based on the output of flip-flops. But you have to be careful with that last one. You do want your main inputs coming directly from flip-flop outputs to make it into sequential logic design, rather than one way to do it, which is to have a counter cycling through numbers and then do a massive amount of gate logic design to get that to go from the flip-flops into the inputs of the 7-segment display. So that is not exactly the way we're going to do it. That's like a series of logic designs. We're going to use sequential logic designs, which means we're deciding what to make the state of the flip-flops change to in order to go to the next number. So for me, that number is, let's see here. We'll start 0, 2, 6, 6, 1, 6, 4, and then it'll cycle through again. Okay, so let's talk about how we'll do that. So the first thing that you do is you write out your student number, and then you're going to write out the bits in that. So 0, 2, 6, 6, 1, 6, 4 is going to be in binary 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0. That's the second 6. And then we got a 1, 0, 0, 0, 1. Then another 6, 0, 1, 1, 0. And then a 4, 0, 1, 0, 0. Okay, then we need to go back to the start. And right now, you check if there's any obvious simplifications that you can make. So for me, because I don't have any 8s or 9s, the top one is a 0. You may have other obvious simplifications, like we're almost in the situation where these two bits always change together. If it weren't for this one and this one, then you might be able to wire these two to the same number and not actually use a different flip-flop. Okay, that's the first step. Then what you do is you convert that stuff into a truth table. So here, we'll just resize that. So you make a truth table to figure out, given the current state, what are you going to go to for the next state? And we're going to use JK flip-flops for this. So what we'll need is not just the truth table for the JK flip-flop, but the excitation table. So I guess you could say the next step is to figure out the JK flip-flop excitation table. So that is, if we have a JK flip-flop and we are at a 0 and we need to go to a 0, then there's two different things you can do. You can either hold, or you can reset. So let's talk about that. So here's the JK truth table. This means if J is the input, J is input 0 and K input is also a 0, then what we're going to do is hold. If we give it 0, 1, we reset. If we go 1, 0, we set. And if we go 1, 1, then we toggle. So this is a great thing to look at if we're using sequential logic, if we're doing sequential logic analysis. So trying to figure out, given what the flip-flop configuration is, then what's the timing diagram going to be? But what our task is now is to figure out the timing diagram that's going to make the chip cycle through these things. And for that, we're going to need the excitation table. So here's how this goes. You first lay out your states that you need to be in over here, 0, 2, 6, 6, 1, 6, 4 for me. And then if we're in the state 0, the next state is going to be a 1. So that means we need to take Q2. I just numbered the flip-flops 0, 1, 2 here. So Q2 needs to go from a 0 to a 0 for us to cycle between the numbers 0, 0, 0 and 0, 1, 0. Q2 stays the same. And that means that you need to give it inputs J2 and K2 to make us go from 0 to 0. This is the input required. In order to go from a 0 to over here, the next state of a 0, you need to, from the excitation table, if we're in state 0, we're going to go to state 0, then you either can reset or hold, which, looking up here, means that you get j has to be 0 either way, but k could be a 0 or a 1. It doesn't matter. So we're going to have j2 must be a 0, and k2 must be can be anything. Let's do another example. So we'll figure out what the inputs to flip-flop 1 have to be in that state. So if we're in state 0, 0, 0, and we want to go to 0, 1, 0, then we need to go from a 0 to a 1, which according to our excitation table means that j has to be a 1 and k can be anything. So that's how you get that state. And then we go along and we do that for all the different inputs. Now let's talk about Q4 and Q5. So what the heck is going on with this? Well, this is a way to keep track of the repeated digits. So the problem is, if we are at a 0, then we don't know whether if we're at 0, then we're definitely going to a 2 next. And if we're at 2, we're definitely going to a 6 next. That's because 2 only shows up once, 0 only shows up once. The problem is, I have 3 6s. So if we're at a 6, then we might end up going to 6 next. If we were at this 6, so this 6 needs to translate to that one. But this 6 should transition into a 1. And this 6 needs to transition into a 4. So sometimes when you're at 6, when the state is 6, you need to switch to a 6. Sometimes when the state is 6, you need to switch to a 1 next. And sometimes when the state is 6, you need to switch to a 4 next. Which means just the output number isn't enough state information to know where we really are. Although there's 3 output 6s, there are really 3 different states. There's the first 6, the second 6, and the third 6. So what you do is you add 2 more flip-flops to keep track of which state that is, which one of the 6s you're at. So here's how that works. If you are at the first 6, we'll have Q4 and Q5 outputting in state 0. If we're in the second 6, we'll make that 0, 1. And if we're in the third 6, then we'll make that a 1 and let's say don't care. Okay, because we don't have a fourth 6. Otherwise, we would have to make this 1, 0 and then 1, 1. Now, it's up to you what these counter ones do in even those states and in any of the other states. If you wanted to make it go 1, 1, 1, 0, and then 0, 1 or something, or 0, 0 for the third one, that's up to you. Totally fine. And in the other states, you can make those whatever you like. So I've chosen to make them don't care, which is a little bit more robust for the starting condition. This means that if we're at 0, 0, 0 and anything for Q4, Q5, then I've made sure that the logic is going to go to a 0, 1, 0 next. But you could decide with a little bit of hindsight to make these something different in order to make the truth table a little bit nicer later on. So that's sort of an advanced design choice that you could make if you like. Anyway, now that we've got the 5 different input variables, we can figure out across the entire table what we're going to need for j and k. So with 5 flip-flops, meaning 5 inputs, because we've got 5 different pieces of information about the current state, so the output of all of them is the current state, then we end up with 10 inputs that are going to determine the next state. So each of these, to figure out what they need to be, we go through this table here, just looking at the excitation table. For instance, if we're at a 1 and we want to go to a 1 with Q2 here, then from the excitation table, we need to set j and k equal to x and 0. So let's go across that. J and k for Q2 need to be x and 0. There's that, to go from 1 to 1. Which other one could we do? Here. So if we are at a 0 for Q4 and we want to go to a don't care, then it doesn't matter what we make J4 and K4 because we don't care what we go to next. So we have 2 don't cares there, which is nice. But the problem with that is if you don't care what state you go to next, then you can, it is a little bit obnoxious when you go from a don't care state to another state, because normally the excitation table always has a don't care, right? So if we are at a 1 and we want to go to a 0, then we don't care what j is, k can be a 1. The problem is if you don't know what state you're at, then you don't know, then you can't use, you don't know whether hold or toggle would be the right thing to do. So you only have the set and reset options, right? If you want to end up at 0 and you know you're at 0, then you have 2 options. You can reset or you can hold. But if you know you're at 1 and you want to end up at 0, then the 2 options are to toggle or reset, right? So reset or toggle rather than reset or hold. So Not surprisingly then, if we are going from a don't care state to a specific value, then we have to set both j and k. Neither of them is a don't care state. So that can be that's sort of a disadvantage of having don't care states in the input variables there. Okay, so that's how you get this table. Now what you're going to do is come up with a truth table for each of these different values. So let's look at J2 here. So this is there's 5 inputs, right? So Q2, Q1, Q0, Q4, Q5, as I've called them. So these ones are labeled like this because they're associated with the actual counting variables, and these ones are the number variables, the numbers that we're outputting, and these ones are just for keeping track. So they're not going to output to the 7-segment display afterwards. So you see here are the ones that are going right to the 7-segment display. You can see the trace of those that comes from there. This one outputs as that's Q2. That's Q1 bar. I was confused there for a second. This one outputs to there, and this one outputs to there. But the last one is just tied to 0. These two outputs don't go to the 7-segment display. They're just for keeping track of which state we're in. Okay. So we need to transform this data into a truth table to figure out what the logic is. It turns out that we're going to end up with J2 can be tied to Q1 or Q0. Or we can use Q1 bar NANDed with Q0 bar. Remember that with the flip-flops, we have the bar outputs as well. Every flip-flop outputs both the value and its inverse. So it doesn't take any more gates with flip-flops to get the inverse of the value that we wanted. All right, so we've got a 0 in the state Q0, 1, 2 is a 0. And here, the table's laid out with the counter ones along the left here, and Q0, 1, and 2, the actual timing ones along the top. So this is a 5-input K-map style. We've got, I wonder if I can design the border layout here. Maybe it's in the home menu. Border, yeah. So, well, that's draw table. So I wonder, yes. Draw table, is that it? Doesn't let us do that. Okay. Borders. Design. Border painter. Is that it? I think I need to select a thicker border here. There we go. Okay. So that's how you figure out what where the border painter is, and that's basically what we're going for here. So that is to signify that we've got a separate left and right here. You see I got a little bit fancier at the bottom here, and maybe a little bit lazier. Okay, and there. Great. All right, so what we're trying to get at with these K-maps is a different, sort of like a stacked thing. This is how you deal with a 5-input K-map. You picture this whole thing on top of this whole thing, and what's changing is Q2. So this one is Q2 equals a 0, and this one is Q2 equaling 1. So this, from this spot, you can, if you want to change Q0, then you go to the right. If you want to change Q1, then you go to the left, which wraps around to this one. If you want to change Q4, you go up, which wraps around to here. If you want to change Q5, you go down. And if you want to change Q2, then you go in or out of the page over to this one. If you have a 6-input K-map, then you would have your other one. You could list your other one down this column and imagine that there's sort of like in or out. You might stack them like this one, then one down here, and then one down there, and that would be your 6-input K-map. So you picture in 3 dimensions that other thing. All right, so we've got J2 has to be a 0 if we have 0, 0, 0, and anything for Q4 and Q5. That actually gives us 4 zeros like this in the table. J2 has to be a 1 if we have 0, 1, 0, which is over here, and anything for Q4, Q5. Then we don't care what J2 is for this case, so let's not bother with it. And J2 is a 1 for 0, 0, 1 and anything, which is this case. So we've entered a 0 for that case, our 1 for that second case, and this 1 for that case down there. Everything else that we didn't enter was a don't care case, because either J2 is in a don't care condition for that input, or the input can't happen. So that means we end up with the rest of the whole boxes equaling x's, and we can come up with a pretty simple sum of products, or rather a product of sums implementation. So this one and this one boxed together would be the K-map boxing, and that gets you to let's see, Q2 can change, Q4 and Q5 are all we have all the values for those two. So the only things that are fixed there is Q1 and Q0, and they both are at a 0 to give us this 0 output, which means by product of sum stuff from K-mapping in the regular way, we end up with Q1 or Q0. Remember, you sum up the inverse of the states that you've got there in the K-map for product of sums. So that is how you figure out that the input to J2 should be a single OR gate. Once again, the steps are: list out your student number, eliminate any variables that you can with simple tricks to get rid of a flip-flop, then lay out the states that you have, use a counter set of flip-flops to keep track of the repeated digits, go through the excitation table to figure out what the J's and K's have to be to get you from one state to the next one, and then for each J and K setup that you've got, draw your K-map and use that to figure out the logic. Then from there, so you repeat that for all of them, right? So you get your K2, J1, K1, etc., and we end up with some logic. So then what you want to do is summarize your logic, and if you look across, so I mean, if you want to practice some more, take a screenshot of this, and then look across the different K-maps, K2, J1, K1, J0. This document's going to be online if you want more practice. At the end here, really these ones are all X's. What I did when I started copying the table was I noticed that actually the a lot of the input states don't happen. So if you look across this table here, you think about all the different possible input states we have, and you might want to draw that out in a little bit more detail to make stuff work. So 0, 0, 0 with all don't cares there is, we figured out this column. 0, 1, 0, and then don't care is this column. 1, 1, 0, 0, 0 is one specific cell. So that is this cell, right? Then we've got 1, 1, 0, 0, 1. That would be exactly this cell. 1, 1, 0, 1 don't care is both of these cells. So things get a little bit tricky when you're on those repeated digits. While repeated digits can be good in that they eliminate the number of flip-flops that you have, so the non-repeated digits kind of mean that you need more flip-flops, but the repeated digits can be sort of complicated in terms of the don't care conditions that you get. Okay, so again, you summarize all your logic there. Then you think about designing it in a way that you have a simple gate implementation. So I optimized this a little bit and managed to get it down to 1 or 1 NAND. It's good to think about different options in case you need one thing a little bit more easily than something else. So K2, we ended up with this. And then this looks like sort of a strange way to write it, but, whoops, one sec, house is burning down. Okay. So a bit of a strange way to write it, but what we have is the you have to consider all of the other things that you're going to need. So down here at J0, we wrote this in a certain way where we have Q4 nor Q5 bar. And so you think, okay, well, should we use an OR gate and an AND gate? Or written like this, we use an OR gate and a NOR gate. Down here, we just can use that exact same thing. So since we already have it up here, we have it for free when we need it for this when we need it for this thing. So that tells us we just want to AND that thing and that thing, for instance, which is equivalent to having this and then inverting it, and then there we go. Okay, so yeah, that's just some simplifications that you can think of doing. Up to you how much you want to simplify it. And you probably do want to spend a bit of time trying to simplify it, because once you go and wire it up, it's going to be pretty complicated and easy to mess something up. Consider also optimizing for the kind of gates that you're going to have to use when you go and build it on a breadboard, since the gates come in chips of 4 for the ones that we have. So the 2 input gates come 4 to a chip, so we can get 4 NOR gates pretty easily, 4 OR gates, and we needed another one, and we just used the NAND for that. No worries. All right, so that's basically an overview of how you do the design project. Thanks for watching.